covers a very famous concept from algebra, the Dijkstra algorithm. We basically developed a little game that includes the Dijkstra algorithm solved by a human person, but how exactly and why we choose the Dijkstra algorithm comes a little bit later. What we definitely wanted to find out is an explorative study for understanding the individual EEG signals for the interrelation between task difficulty and motivation. So in other words, how do the EEG signals actually change for a person once the task difficulty rises, and can you derive somehow the motivation from that, or where's actually this maximum motivation point? The question that first comes to your mind, why we wanted to do that study, and it is quite simple. None of us has ever used EEG. We had no clue a week ago about how EEG actually works, what data you get out. So we wanted to mainly understand what is and how does EEG work. That was the big question for us. But with that in mind, there's some research background that we want to also present why the studies could be actually also interesting from a research perspective. And there's a theory called the motivation intensity theory. There's a relationship between the task difficulty and the effort that you put in. Basically, the harder a task gets, the more effort you will put in. When the task difficulty is quite low, you're quite bored, you are basically sleeping, you do the task while you're sleeping. When the task difficulty gets a little bit higher, your performance gets better, you get more challenged, you want to achieve more, and this goes to a certain point, and once this point is actually reached and the task gets too difficult, your motivation declines rapidly. So if a task is too difficult, if a task causes too much arousal, too much stress, you're actually not performing properly enough. And I guess everyone had this already. For example, back in study times when you needed to write exams and you were studying and studying and studying and just felt overwhelmed and stressed by everything, your motivation and actually your performance was not good anymore. But once the motivation was too low and there was not enough pressure, you also were not learning properly, maybe at the beginning of the semester or trimester, whatever you had. So it's actually good to have some task difficulty, some stress level to have a good performance. And that's why we wanted to find out what is actually how do we actually find this point where you have the highest task motivation, so where you have the highest motivation to do a task, to perform well. And we wanted to see if you can see this point in an EEG signal. And why is this a challenge? It's a challenge because people are very, very individual. There are people with different backgrounds, different preconditions, different capacities, different experiences, different trainings. They are very, very diverse, the people. Everyone has their own brain, luckily, and no one has a connected brain to some overarching brain entity. No, everyone has their own brain. Everyone has their own capacity. Everyone can handle different amounts of stress. Some have maybe other backgrounds or are already going stressed into a situation. How do we find it out? We employed an EEG headset, the Unicorn headset, exactly. And we were looking at the time series of data, especially, or frequency data, especially on the beta, alpha, and theta waves. The delta waves we don't have yet because I thought no one will be sleeping, or we thought no one will be sleeping during experiment. At least that's what we hoped.
Hi guys, so I was mainly involved in the development of the project. And like he explained, we created a task with an easy and a hard difficulty, and I'm going to talk about the task. So the task is basically, before that, let's talk about what kind of tools and technology we used. And so we used a Unicorn 8-channel EEG with dry sensing, so we can just get the EEG signals in a very simple way. And then we, of course, used the Unity game engine to make our simulation, and then after the start of the simulation and the end of the simulation, basically it gets saved into a CSV file, and then using a Python script we can then visualize the data, and then we can infer something from the data. So I'll talk about before talking about the task again. These are some of the snapshots from our experiment. And here in the left, you can see Tim wearing an AG cap. Thank you for your participation and headset. And then trying to solve a task here in the screen. If you see, it's a graph. I'll talk about it more in the next slide. And these are the snapshots. And so yeah, now let's go to the task. So the task is very simple. So given a weighted graph, you have to find a shortest path from start to end. There might be a lot of possibilities, right? You can go this way, you can go this way, but now you have to do some calculations in your brain and then try to figure out which one is the shortest path. So that was the task. And as the number of nodes in the graph increases, obviously it becomes harder to find the shortest path in the graph. So this was the task. They were using just controllers, not a lot of movement, like this, so that it doesn't interfere with the EEG data. And then they were tracing out the shortest path. And so why we could have used any other task that is like hard or easy or hard. There could be many, right? So, but why did we choose this? So we choose this because first of all, it involves using of working memory. So when you're tracing the path, you have to use your memory for what you traced behind, and also it uses the attention, and also it uses decision making. Then after each trace, you have to decide where to go based on the weight of the edge. So it involves a lot of this decision making and also high level processing where you have to plan, organize, and execute. So this is why we chose this task, hoping that it could give us some meaningful results. And then yes, after the experiment, we only used one participant because of the short amount of time that we had. And then we recorded his EEG signal, and this is what you get. And it's not exactly clear what is happening, but we can actually infer slightly that. So if you're doing an easy task, research suggests that there has been finding in research that you emit more alpha waves, and compared to when you're doing a difficult task. And in this graph, you can see, although it's not in the same range, but you can see that in the easy one, there appears to be more alpha waves than the hard ones, than the medium or the hard graphs. And also you can see the interval between the peaks are different in the hard ones. We exactly don't know what exactly is happening there. And maybe Dominic, you want to add on this?
Yeah, but basically we were just looking at that, and that was one of the things that came to our minds, that we saw quite some intervals between the peaks. Of course, there's always alpha, beta, and theta waves for all conditions, and approximately at the same time because the brain is active at those moments. But especially in the medium one, we saw Tim took some mental breaks in between, actually. So we were quite surprised about that. We don't know yet if this has anything to do with actually the motivation or the task difficulty. But that's definitely a point where we would continue in the future to put attention towards, especially once we add more difficulty levels. It was so far just 2 difficulty levels. Even the medium Dijkstra one was quite easy still. I guess, Tim, you made it quite fast. It was, I guess you needed 17.5 seconds, so that was still quite fast. So if we add more difficulty, how would it change then?
It's also, yeah. And also, last thing that we forgot to mention was, so there's, based on the literature out there, if we take a fast Fourier transform of the theta waves and add them together, fast Fourier transform of the alpha bands, add them together, and this is what the ratio comes out to be. So we believe that it has something to do with like the difficulty, which is again which actually makes sense, yeah, but still there's like a lot to understand behind this data. I'll actually like to call Mario.
Hi everyone, I'm going to show you some EEG wavelets. This is a sample of your EEG when you're asleep, so they are a bit taller and they have more space between each wavelets. But when you wake up, but you're still not really using your brain much, they become shorter, and when you are awake and have some mental activity like doing this game, then they become denser and shorter again. So what we really wanted to understand was if we make the task more difficult each time, what happens to this pattern? These are the steps that we would like to take in the future with this project. So we need to do more user studies, and we need to enhance our application so that users can work with it easier. And we would like to have more data from different users and different age groups. That will help us to analyze the data better. And we would like to keep the motivation of the users high through the application, so that will need lots of UX research, and we would like to know how users perceive such kind of applications and what they think and how they interact with it. The learning curve. It was really hard trying to understand EEG signals for the first time, because we were new to it and we didn't know what it means when we were looking at the wavelets. They were just some lines. And the documentation of the EEG signals, for example, the unicorn and the OpenVibe, were not helpful enough when it came to finding the right filters to filter the noise of the wavelets. And connecting the signals to Unity was relatively easy. Filtering data became easy after we gave up OpenVibe and we started using Python. So it was much easier with Python filtering the data. We were a bit scared of physiological data because we didn't have any information about them. That fear is gone by the end of this project. That was it for us, but if you want to try to play that game, we have set up a place for you to try it. Thank you.